Okay, welcome to the second class of Don't Trust the Science. This is the second class because in the first class I dealt with Einstein and why I don't find him very convincing. I actually think he was kind of a fraudster, if you ask me, okay? And so I think that this is important. I think we should actually doubt some of the things we are told at school. I really do. I think we're told a lot of rubbish at school by our teachers, and it's not their fault necessarily. It's just that they have learned mistakes as well. And a lot of the time in today's world, we like to rely on experts. We like to outsource our thinking and let experts decide what's correct or what's not correct. And so we rely on things which perhaps don't even make sense to us, but somebody says that it makes sense. Somebody says that it's logical, it's true, it's rational, and we take their word for it. And I think that this is a good word for this would be scientism, a kind of religious scientific faith. And I say religious because you're not allowed to question the dogma. You're not allowed to say something like the sun might not be a gas. You're not allowed to do that. You're not allowed to say that Saint Einstein might be wrong, okay? And so that's why I'm doing this series, Don't Trust the Science. I actually love science, and I hope that that can come across in these lectures that I'm giving. But of course, you all know that I'm an English teacher. Okay, occasionally I might teach philosophy or Russian, which have nothing to do with spectroscopy. And that's going to be the main topic for today. Because there's a really good channel on YouTube, and I want you all to go and watch his channel. It's a channel called Sky Scholar, and the guy who runs it is called Pierre-Marie Robitaille. I think he's a French-Canadian, and you can see it in the name, can't you? And he is a scientist. To be clear, he's a radiologist or a spectroscopist, and he worked at Ohio University for a very long time. And I wanted to introduce him as the guy who created, because he's a doer, not a talker, he created ultra high field magnetic resonance imaging. He managed to create a device which could give us images inside the body, for example, of the brain, that were at a much higher resolution than anything before. So he created something which was cutting edge science, and he worked with the actual engineering of this device. He's actually a chemist by training. That's what spectroscopists are. They are usually chemists. And this particular device is used, as far as I know, it's used in many places around the world, hospitals, so that we can actually see inside the body and so that we can help our fellow human beings. And I just wanted to say that before anybody calls the guy a crank or a weirdo or something like that, because he's clearly done far more for humanity and for science than most other people, perhaps than anyone else that I know. So, you know, you want to be careful calling this guy a crank. He actually does stuff, not just theory, he does stuff practice, yeah? He does practical things with his hands, and he's made things which have made the world a better place. Now, he's a spectroscopist by trade, which means he studies how light and matter interact. That's what spectroscopy is. We look at how different substances react when we fire different frequencies of light at that substance, and the substance might absorb the light and then emit more light. That's what it usually does, something like that. And we study the emission of light after it does this. And it was something that I actually did at university. At my university, we had an NMR spectroscope, that's nuclear magnetic resonance spectroscope. We had an infrared spectroscope, an UV spectroscope. We had lots of different spectroscopes, and each one was for using. Well, you would use it with different substances, because different forms of spectroscopy would be very good at analysing different substances. Very often in spectroscopy, you're doing analysis. You take an unknown substance, you don't know what it is, it's just a transparent liquid in a little vial, you put it in the spectroscope machine, and then you get a graph of the different light that it has emitted or absorbed, yeah, that kind of thing. And by looking at that graph, you already know that hydrogen emits and absorbs at this frequency, and at this frequency, and at this frequency, so you can see what different elements are inside the substance, or maybe even what different molecules you often use the NMR spectroscope for organic molecules because it would be very good at understanding the different types of bonds. Maybe you'd have a methyl group and it would be spinning like that, or going like that. There were lots of different types of movements that it was capable of, and each movement would have a different frequency on your graph. And so you could use your graph for finding out exactly what was in that substance. You know, organic compounds, there are a lot of different types of organic compounds, all with different functional groups in different places. And this spectroscopy was really good at analysing, at finding out exactly what was there. So that's what spectroscopy does, but it's also used in imaging, and that's how this scientist, well, that's what he excelled at. He managed to make this particular device that gave better resolution, better images inside the body than anything that was possible at the time. And I think this was about 1995 to the year 2000, it was about that time. But since then, he's been doing other things, and he's written a paper, you can find it online, 40 lines of evidence for condensed matter, the sun on trial. And you can find this easily, it's free, he gave it away freely, he even sent it to a lot of his colleagues because he wanted them to read his paper. And the main argument is the sun is not a gas. Yeah, we all learn at school that stars are big, hot gases. And okay, they're gaseous plasma, sometimes they're called gaseous plasma, but they are called a gas. They're not called condensed matter. And condensed matter means liquids or solids. That's what condensed matter means. It means matter which is condensed together, bonded together. Gases are not bonded together, so they're not condensed matter. But liquids are bonded together, and solids are even, well, often, not always, even more closely or even more tightly bonded together. So condensed matter, he means liquids and solids. But in particular, he wants to say that the sun is a liquid. And I think that he's got a very good argument. When you read his paper or when you listen to him discussing this idea, I think he's got a superb argument. I think it's very hard to disagree with him. Now, he points out firstly, and this is perhaps quite a difficult point to understand if you haven't studied spectroscopy before, but he points out that it's gases that give you a discrete spectra. They give you a discrete spectrum. They absorb or emit light in different bands, and some of you might have seen this with the early Fraunhofer lines, which was when early scientists, they got a spectrum of the sun. They got the spectrum of the sun, and they noticed that in this solar spectrum that went through all the colours, there were dark patches. And what they understood was that those dark patches, they represented different elements that were absorbing the light which was coming from behind them from the sun. These elements, these gases, and like hydrogen, helium, sodium, but these were in the gaseous form. These hydrogen in the gaseous form would absorb this light in particular bands, and not just hydrogen but other elements as well, all the other elements. And we see these in Fraunhofer lines, and that's the spectra that we see from gases, and we call these discrete spectra because it's only at certain parts of the frequency, it's only at certain frequencies that they absorb the light. Now, liquids and solids don't give discrete spectra. They absorb and emit light in a continuous spectrum all the way along the spectrum. Okay, so you get instead of seeing these bands where light is emitted or absorbed, you actually get a continuous spectrum, and it means that the sun produces a continuous spectrum too. And the Fraunhofer lines are just what you see. They're where the gases have absorbed it from that spectrum, from the continuous solar spectrum. And so he points out firstly that, yeah, it's liquids and solids that produce a continuous continuous spectra. It's not gases. Gases will usually produce this discrete spectra. So it ought to be a little bit strange straight away that the sun and other stars produce continuous spectra, as do light bulbs or something like that. And something else that produces a continuous spectra is black bodies. Now, I'm not going to go too into detail on black bodies. It's a very complicated topic, and it's, again, something that was investigated a long time ago. But basically, they got a black box, and they wanted to look at the thermal emission spectrum that was coming out of that black box. They wanted to well, they measured the different frequencies that came out of that box along with temperature, okay? And it produced this very similar continuous spectra. Now, black bodies are nearly always made with a certain substance, because black bodies, they need to be near perfect absorbers. I mean, they want to be perfect absorbers. A perfect black body absorbs all the light that goes into it. And certain substances actually make better absorbers. Silver is a very good reflector. Yeah, it doesn't absorb. But graphite, something like lamp black or graphite, lamp black is similar to graphite, carbon black sometimes it's called. Graphite, as we all learned at school, has this particular structure, and it's a near perfect absorber. It has this hexagonal planar structure, yeah, where you see it, we learned at school that the carbon atoms are all in hexagons, and they have 3 bonds, which means they've got a spare electron. Each carbon atom has a spare electron, and that spare electron becomes part of a sea of delocalized electrons. And these hexagonal layers, they end up as layers with the delocalized electrons traveling around that and around them, and they're delocalized, so they're not held in any particular place. They're able to travel throughout the whole lattice. Okay, so that's the structure of graphite, and graphite is a very good conductor because of these delocalized electrons. The electrons can move, and that means you can have an electric current passing through graphite very easily. And it means that in certain, when they talk about things like graphene and things like that, they talk about superconductors. It's an even better conductor. It's excellent at allowing electrons to pass through it, allowing an electric charge to pass through it. Now, a long time ago in 1935, a couple of scientists, Wigner and Huntington, proposed metallic hydrogen. So they proposed that hydrogen could become metallic under certain very high temperatures and pressures. It could actually reach this metallic hydrogen stage. And they suggested that perhaps it has a similar lattice to graphite. Yeah, perhaps it looks similar to graphite. Perhaps it is hexagonal planar with a sea of delocalized electrons as well. Okay, and now recently, what we all grew up learning, yeah, that the giant planets Jupiter and Saturn are gas giants. But recently I have been reading in a lot of papers that now we're talking about liquid metallic hydrogen cores in these planets. And I find that interesting. They've gone from being gas planets to liquid metallic hydrogen planets. I find that absolutely fascinating, and I think it's certainly very relevant to what we're talking about today. And what's useful, why might we be interested in thinking about the sun being made of liquid metallic hydrogen and having a hexagonal planar structure with a sea of delocalized electrons? Well, one reason is you have intercalated compounds with graphite. Intercalation is possible with graphite, and what intercalation is, it's putting other atoms between the layers of graphite. You can actually fit other atoms or molecules in between those 2 layers. And intercalation means that we can have a reason for why there are other elements, because it's not just hydrogen and helium which makes up most of the sun, and certainly it's hydrogen that makes up most of the sun. There are all the other elements in the sun, as we know from the Fraunhofer lines, yeah, that we get all the other elements there as well. And I would suggest that perhaps that's because the sun makes all of those other elements, that there's some kind of fusion process that means it can make all the elements inside it. Now, the heavier elements seen in the solar spectrum, yeah, so like iron 13 or something like that, these you get iron, you get calcium, you get magnesium, all these heavier elements are intercalated between the hydrogen layers. And this would be, quite a nice way of explaining it, because it would give us a reason for solar activity. For example, solar flares, coronal mass ejections. We know that the sun throws out a lot of heavier metals all the time, as well as hydrogen and oxygen and all sorts of other things. We could put these processes down to exfoliative processes. Yeah, when even graphite, when it's intercalated with compounds, if you put energy into that, it can suddenly cause exfoliation of the of the elements that are between the layers, where they suddenly come out or they go straight into the gas phase. And this can be an explosive process like we see on the sun. And so it will give us a good explanation for these exfoliative processes. It's a degassing of the intercalated regions of these heavier metals that are in between the layers. Okay, and so that's why perhaps this liquid metallic hydrogen with this hexagonal planar structure is perhaps a very desirable model, or it's a good model. It helps to explain a lot of what we actually see all the time when we look at what the sun is doing. Now, please, I'm just giving you a really, obviously, as I say, I'm a grammar teacher, and it was a long time since I studied spectroscopy, and obviously my understanding is really limited. But I thoroughly enjoyed his PDF, so please do go and have a read of it and see what you think. But there are a lot of different arguments, 40 different arguments, for why the sun must be, or is more likely to be, in the liquid state rather than in the gaseous state. Now, he mentions also solar granules, for example, and we've all seen this. You've seen those really close-up pictures of the sun's surface, and you see these solar granules there, and these solar granules are clearly showing Rayleigh-Benard convection cells. You can look this up if you want, but you can look up lots of different experiments showing this aspect of fluid thermodynamics. This happens with fluids, with liquids, and it's where you see this convection cells. Yeah, the sun looks like it has this on its surface, and this is something, it's a surface effect. It's where you have a liquid, a fluid, and the convection cells look like that. And so surely, if it's got fluid convection cells driven by fluid thermodynamics, how can it be a gas? Surely it's a liquid. Secondly, the sun has a shape. It's slightly oblate. Now, of course, gases don't have shape, and so you have to say that the shape of the sun is just apparent, that it's not real, that the surface of the sun is not real, it's just an apparent surface, because a gas doesn't have a surface, right? And so if the sun has a real shape and a real radius, and we do measure the radius to extreme precision as well, how can it be a gas? Surely gases only have the apparent surface. Surely only the sun in a liquid state would have a real surface and a real radius. Now, what other structure can we see on the sun? Because, of course, if the sun's got structure, it's hard to say that it's a gas. Well, firstly, the solar rotation varies with latitude. It takes a lot longer for the surface of the sun at the top to go round in a circle, to do a complete rotation. It takes 30 or 35 days at the poles, and it goes much faster at the equator. It only takes 25 days for it to rotate at the equator. So this shows that there is some structure to the sun, and it is hard for me to imagine that we would have differential rotation if it were a gas. This differential rotation where it's rotating faster in the middle and slower at the top. And so that's some form of structure that seems to make it look like it has a real surface. Perhaps it's a liquid, perhaps it's a solid, but some kind of real surface. And I happen to think that liquid is a much better suggestion, because I'm sure you've all watched those videos, where that coronal mass ejection fires out, and quite often you'll see the coronal mass ejection fall back onto the surface of the sun, and when you do, sometimes you all even see these ripples going out, just like ripples on a pond. You see transverse surface waves, and you get transverse surface waves in liquids, in ponds, in the sea. We've all seen those ripples before. Well, I challenge any of you to look at some of those amazing videos that we now have on YouTube, for example, but anywhere you like, look for those videos of the sun being active and throwing stuff out. To me, it really does look like a liquid rather than a gas, and that's just my opinion. Of course, it's just opinion. Now, it also has a magnetic field. Now, can you get a magnetic field from a spinning gas, or do you need it to be condensed matter? It seems to me that the charge needs to be condensed. It needs to be to get this dynamo effect where you produce a magnetic field. I don't think anybody in the lab has ever spun a gas around and managed to get a magnetic field. Now, I know, there are perhaps things which I am missing here, obviously. As I keep saying, I'm not a scientist, but to me, it's much more likely that you get a magnetic field from a spinning core, which might be solid or it might be liquid. Yeah, but from something solid or liquid spinning. You also get coronal rain, where you see stuff coming back down from the corona. You see coronal loops. Yeah, this is all structure. It's not something which you often see or you often associate with gases. You get these splashdown events that I just mentioned, where things seem to hit the surface of the sun that have just been expelled and then cause these rippling effect. And then, of course, you have the whole science of helioseismology. Now, for me, and perhaps again I'm being a bit stupid, perhaps seismology has got everything to do with gases. But for me, I usually associate seismology with the Earth and going through solid, going through something that is condensed matter. I find it hard to think of a seismic wave in some kind of gas. It's usually associated with solids or maybe liquids, but it's hard for me to think that something can oscillate, that we can have these sound waves traveling in its interior, bouncing off a surface, yeah, a real surface, because only a real surface things can bounce off. You couldn't have it bouncing off the apparent surface of a gas. And so how can the sun oscillate? How can it have these oscillations inside? Surely these require a physical boundary to sustain oscillations. And so that's all I have to say really about this. If you're interested in Pierre Robitaille's work, you can look up his paper online and have a read through it, or you can go to his YouTube channel, which is perhaps a lot easier to understand. There's a load of different videos on there on a lot of different topics. But I've found his arguments really convincing, and so this is another thing which I don't particularly trust in the science, which is, I'm not so sure that the sun or other stars are gases. I actually find it a lot easier to understand if I consider them liquids. It's much easier for me to understand what we're actually seeing when we look at the sun, and to me it really does look like it has a liquid surface when I actually watch the different processes. Liquid plasma, sure, because plasma just means that the charge is delocalized, and so really metals, you might argue a metal is a plasma because a metal has a sea of delocalized electrons. So you can even have solid plasmas. But when I look at the sun, to me, it does look like a liquid. And so what do you think? Let me know. Tell me under the video. And I'll be coming back very soon, I think, with the third class of Don't Trust the Science, because I've got some other things which I'm not so sure are true. Anyway, I hope you all enjoyed that. I hope you'll enjoy the next one. See you all soon.